Hello, good morning or afternoon or evening, everyone, depending on where you are. And welcome to today's webinar on modeling softwares for transient flows. My name is Caterina Capponi. I'm Associate Professor at the University of Perugia in Italy, and I'm delighted to serve as chairperson for this session. We have a great lineup of discussion ahead. We are at the 4th day of webinar, and today we will focus first on the InfoWater Pro software by Autodesk, and then after the coffee break on 2 open source Python packages for modeling transient and water networks. There will be some time for question and answers at the end of both presentations. And today I'm chairing this session with my colleague Valentina, please.
Sure. A warm welcome also from my side. My name is Valentina Marsili, and I am a research assistant at the University of Ferrara in Italy. It's a pleasure to be co-chairing this session of the first IAHR online transient course on modeling software for transient flow. I will be very brief, but I would like to express our gratitude to all the sponsors and supporters that made this initiative so successful. So an heartfelt thanks goes to our sponsor, Delta RS, Bentley, Power Vision, and Simpson. We are also grateful to our supporters, Hydropower and Centro Studi Sistemi Idrici. Last but not least, do not forget to use the Q&A box that is available at the bottom of the page. Okay.
To start us off, I'm pleased to introduce our first 2 speakers. Sean Wang brings extensive experience in water and wastewater systems with a strong background in numerical simulations. Currently, as a software development manager at Autodesk, he oversees the development of water system simulation products, including InfoWater Pro and InfoSurge. Join him is Nathan Gertz, as a product manager in Autodesk's water infrastructure team. With nearly a decade of experience in model implementation and operational modeling within WISE, Nathan specializes in water distribution products and their real-time applications. Together, they will guide us through an insightful presentation on transient modeling using InfoWater Pro, its challenges and effective surge protection strategies. Sean and Nathan, over to you.
Thank you, Katerina. Yeah, so we will be covering water hammer in water systems. So we are focusing on water distribution systems. Naturally, is our area of experience, and we'll be looking at analyzing and mitigating water hammer and surge events using a software called InfoWater Pro. Throughout this talk, we may interchangeably use the terms water hammer or pressure surge events or hydraulic transients. Those are all kind of similar terms that we hear in our side of the industry. So a quick overview of the agenda. We'll discuss the background, which I believe many of you attendees of these series are going to be somewhat familiar with in terms of hydraulic surge events. We'll dig into some of the theory. We'll bring up some common pitfalls, as there's some conventional experience that sometimes is can actually go against the proper theory you should be following. So watching out for certain pitfalls, and then we'll show how you can model these events and mitigate transient events in InfoWater Pro, and then finally share out a call to action with some additional resources. So that is the agenda. And you already heard a quick introduction of the two speakers. Fortunately for all of you, Sean will be presenting most of the technical content, and so we can move to the next slide. So getting into just some overall background on surge hydraulic events. On the next slide, you've probably already been learning obviously a bit about the theory from the previous days, but hydraulic surge events as a study has begun in the 1800s with classical research beginning by Michau. And this is when the research really started to emerge, and the Joukowsky equation was founded during this time. This kind of became one of the kind of fundamental foundational equations used for quite a bit of time, and it's still used today, obviously as kind of the most simple representation to understand the impact or the magnitude of the pressure spikes that can happen. And then it was during the 1900s that theoretical mathematical analysis began to advance with computation. And this is also when physical experimentation and verification continued. But it was really during the 2000s that commercial computer models continued to make advances to really solve hydraulic surge analysis at a scale where you can use it for real world systems. And there's also been a growth of field instrumentation that can capture surge events with pretty good accuracy, and then use that for model validation. So that's where we are. What is the challenge? Where I come from, or in North America, I often find that in many of the core civil engineering backgrounds, there's not much coverage of surge analysis in some of the core degrees for water resource engineering, and there are also sometimes some conflicting guidelines that you hear. It's sort of a narrow topic that not as many people go into, and it's also a complex topic, and so there can be different approaches and guidelines that you might hear. And one of the dangers is that a little knowledge can be a dangerous thing. This is a quote that we had come across that we can find is true. If you know a little bit of the theory, you can assume you can go in and start doing these analyses. But if you aren't aware of some of the implications, you can end up making potentially some mistakes if you're following certain rules of thumb and traditional approaches. And so it's just really important to be aware of that, and how those approaches can impact your final engineering designs. And so that's some of what we plan to come away with is a better understanding of how we can apply tools with confidence. And the consequences, I'm sure you're aware, can be pretty catastrophic. Obviously, a water hammer or surge event can cause extreme maximum pressures, right? When water comes to an immediate stop, it can cause high pressures that can end up rupturing pipelines. They can cause permanent deformation within pipes, and as then water bursts, it causes environmental contamination. Obviously, it can erode soil underneath roads and cause pretty significant disruptions. In addition to high pressure spikes, you can also get very low pressure spikes when the supply coming to an area suddenly cuts off, and it can cause a negative or a very low pressure spike. And this can cause pipeline collapse. Coupled with high velocities, it can cause air cavity formation. Even during the moments that you have low pressures, it can actually allow contaminants to intrude into systems, which is a high concern for water distribution systems. And just in general, when you have these pressure waves moving through, it can cause pipelines to move, which is definitely a disturbance, as well as having vibrations as things move around. And this video, if you can play, Sean, just illustrates, so as we're focused on water distribution systems, oftentimes these systems are running through cities, they're running through towns, and when large pipelines break, it can have a pretty catastrophic impact on not just the water distribution system, but even on whole communities, on traffic, on so many things, flooding homes. And so it is really important when we have engineered pipeline systems going through cities that we have the right tools in place to understand and mitigate these pressure events as they happen, because obviously it affects our water resources, it impacts many different things and including the environment. So on the next slide, we have just a couple historic examples. So just another few examples just to drive home the importance of this. In the U.S., well, these kind of events happen on a somewhat of a regular basis, that certain large failures can occur due to, oftentimes attributed to, transient events. In the U.S. in February 2008, there was a 6-foot diameter water main that failed because there was an uncontrolled pump shutdown. The pump was shut down without the right devices in place, and that caused a sinkhole that was 40 feet wide, 60 feet long, and 16 feet deep. I apologize for any attendees that are that prefer meters. We had created these slides in the U.S., and it resulted in, so this event resulted in 2 million gallons of water wasted. Sinkholes like that, they can collapse in highways and cause huge disruptions to traffic. In February 2012, there was a 13-foot diameter water main that ruptured in Libya. And this was due to a rapid valve closure, and that resulted in 53 million gallons of water that was wasted. In 1950, there was an 8-foot diameter penstock in Japan that ended up failing due to operating errors, the way that it was operated, and this caused 3 deaths and $500,000 in damages. And also in Russia, there was a 20-foot diameter penstock that failed in August of 2009 due to a sudden wicket gate closure, and that resulted in 75 deaths. In that case, it was 40 tons of oil was spilled and 400 tons of trout killed. So these events can be obviously very catastrophic. And so the goal of this presentation is we want to educate you on the theory, some of the pitfalls to watch out for when you're analyzing water distribution systems, and show how one of the tools that we have available can help you simulate and mitigate and plan for these events. And so with that, we both come from Autodesk, and we have 2 different solutions that can provide hydraulic water modeling for water distribution systems. These are often used globally for master planning of water distribution systems, but they can also solve transient analysis. So on the left, we have InfoWater Pro. This is an extension inside of ArcGIS Pro. ArcGIS Pro is a GIS platform provided by Esri, and that's where many cities, municipalities keep their system data. And so that's why it makes it an ideal location to do your modeling, because you can do hydraulic modeling then right inside all of your GIS data. It uses a hydraulic engine based on EPANet. So that's used to solve the flows and pressures throughout your system. It also has a separate engine that is used for transient analysis that builds off of the boundary conditions provided by EPANet. InfoWater Pro has a strong footprint in North America. So you might not have heard of it if you're in other regions, but many municipalities use it in North America. The other software is InfoWorks WS Pro. This is a standalone software. It comes with optional cloud-based services, so you can store your data in the cloud and collaborate with different teams, using the cloud, as well as cloud computing. If you want to simulate multiple different scenarios all in parallel in the cloud, you can do that. It has a custom engine that has been developed over 30 years, used and accepted. It follows obviously similar governing equations to EPNet, but a little bit different approach. It has strong adoption in Western Europe, as well as Australia, New Zealand, and bits of East Asia. InfoWorks WS Pro also uses the same hydraulic transient analysis that's integrated with the full hydraulic network. And so both of these tools use the same surge analysis engine. For today's talk, we're going to focus on InfoWater Pro, but really the same capabilities apply to either product. And so that's just a quick overview of these two products and how we're going to focus on InfoWater Pro. And with that, I'm going to hand it over to Sean to jump into the theory and applications of transient modeling.
Okay, thank you, Nathan. So before I start, I want to emphasize that InfoWater Pro has a user community, and then Nathan and I are highly involved in this technical community to share the knowledge about the transient modeling, and also share users' lessons or tips or tricks with all others users. So because in the US, the water distribution system is some are really large, some are small, and then the water distribution system has a lot of kind of control devices like pumps and valves, and then it's quite different. Okay, so next I will go over the transient modeling theory. So for theory, let us start with the hydraulic transients. So the hydraulic transients are the transient states between the initial state and final state of a water distribution system. And as shown below here, when the pump is on, we are able to see the junction 11's. Junction 11's pressure is at 120 psi. And when the pump is turned off here, the final state, the junction 11's pressure is in 105 psi, which is the final state. So the transient states are the states between the initial state and final state, and then the pressure, the flow, they are going up and down. The typical transient event duration is a few seconds, a few minutes. In some situations, could be up to kind of half an hour. And then the typical simulation time step is a fraction of a second. So next, we can also try to understand hydraulic transients from the perspective of space. So in the right diagram, we are able to see the waves kind of going through the whole network. So they are generated due to the operation of changes such as a pump trip, valve closure, or hydrant flushing. And they travel with the sonic speed throughout the network. And pressure waves are mainly generated at the location of pumps or control valves. As time goes, pressure waves are dissipating gradually. So it means the size of the pressure waves would reduce gradually. And pressure waves are transmit or reflect when hitting a junction, with 3 pipes or even 2 pipes with different material because they have different wave speed. Okay, so next. We can also trying to get a deeper understanding, just combining both the perspective of time and space. So on the left diagram, the y-axis is time here. So we are able to see the delta H1, delta H2, delta H3. Those are pressure waves. Delta H4, delta H5, delta H6. And then the x-axis is the space, is the pipe, it is the distance from the upstream end of the pipe. So pressure waves delta H1 to delta H6, they are traveling downstream from A to B. And then we can see that delta H1 travels 6 times from A to B. And they are dark blue here. And delta H6 only just travel one time step because it has generated, at least time step. And it is in red. So from here, what are the pressure changes at point A and point B? So for the point A, the pressure change is delta H1 plus delta H2 and delta H3, delta H4 and delta H5 and delta H6. How about point B? Point B is kind of downstream of the pipe, so it only receive these delta H1. So the pressure change for point B is only the delta H1. So in other words, pressure waves are generated in a rapid manner. It's generated incrementally, cumulatively, and also with destructive impacts. So when positive pressures wave build up, delta H1 to delta H6, when those pressures add up, it can lead to high pressure spike and then pipe break. When the negative pressure waves build up, it can lead to low pressure, negative pressure, and cavitation in pipe collapse. So what are the events leading to the hydraulic transients in water distribution system? Some are mild, such as a water consumption change. For example, like, there is a sudden change of a event such as in the US, it could be a Super Bowl event causing a lot of consumption increase. It could be just tank level changes. Suddenly the tank just have a huge level change. And some events are controllable. For example, like pump start up, pump shut down, speed up, speed down, and valve opening, modulating, enclosure, and even a hydrant flushing. But unfortunately, some are uncontrollable, such as pipe burst, pump trip due to power outage. So when we do the surge analysis, we would like to focus on uncontrollable transient events, such as pump trip or power outage. There are multiple methods to access the hydraulic transients, such as Joukowsky equation and numerical simulations. But first, let's focus on the Joukowsky equation because it is the easiest way to do the preliminary assessment of hydraulic transients. So first, we need to figure out the wave speed. So the wave speed is a function of pipe diameter, pipe thickness, pipe material properties, and water property, and also the pipe constraints. Next, we can try to figure out the velocity change. We know that the transients are between the initial state and final state, so we need to figure out the initial state's velocity and final state's velocity. So we got the velocity change. And next, we can calculate the estimate the magnitude of the pressure waves. Which is here, the delta H equals C over G. Delta V is the velocity change. C is wave speed. G is a gravity constant. And next, we can assume all waves are generated instantaneously, and there's no wave reflection. So it's an ideal situation. Assume everything happened at the same time exactly. With that, we are able to figure out the maximum surge potential. Could be upsurge, could be downsurge. So the maximum upsurge would be C over G V naught, and the negative potential downsurge would be negative C over G V naught. But usually we have a cavitation limit. Cavitation, we are not able to get down to really low pressure. It's impossible. So it's also a big issue for for the modelers, for the engineer to figure out and then figure out a strategy to mitigate the cavitation. And let's move on to the simulation methods. So usually there are two kinds of numerical methods. So the first method is a method of characteristics, which we call the MOC. And the other one is a wave characteristic method, which is WCM. So let's focus on the MOC first. Either method, we need to solve two equations on the left. The top one is a governing equation, the mass conservation, or continuity equation. The other one is a momentum equation. We need to conserve the momentum, through the system. So for MOC, if you look at the right one, if the right diagram, the right picture, there is a F1 circuit. The F1 circuit is composed of multiple sections, right? So for the MOC, each pipe is divided into, similar to the F1 circuit, divided into many computational units, and each unit is like, one of the units would be like a straight section with a high speed, right, in corner with a low speed, and then a section to connect those two, right, a chicane or hairpins of F1 circuit. Pressure waves are calculated for each computational unit. In the bottom left, we are able to see the x-axis, which is space, and then the y-axis, which is time. And the grid is created in a way so the solution is able to achieve along those two characteristic lines. So because of that grid, we need to reduce the delta x, we need to reduce delta t. So MOC could be very computationally intensive, and it's expected to be pretty slow for the large, water distribution networks. So next, let's talk about the WCM, which InfoWater uses. It approached this problem from a very different perspective. So for F1 race, we no longer focus on the circuit. We put our eyes on the individual race cars and track their position and speed. Instead of focusing on pipes, WCM, wave characteristic method, WCM targets all pressure waves. And all waves are generated and travel along pipes. And wave transmission and reflection leads to more new waves, such as this one. And all waves are tracked in terms of their position, their magnitude, and then how to calculate the pressure at a desired point. It will search for all nearby pressure waves and then sum them all up and to represent, the pressure at that pressure change at that location. If we can see, it sounds pretty easy. Delta H is just equal to, C over G, and delta V, just a simple equation, and just there are millions of, pressure waves, in the system. And it sounds like easy, but, it was proven years ago or decades ago. It was proven is comparable with the MOC method of characteristics. And the benefits of this method is it's really computationally efficient because it only tracks waves. It doesn't divide the pipe into smaller pieces. So it is really efficient. Next, let's talk about column separation or cavitation. So it is an important topic for the transient modeling. So air plays not only a positive role, it also plays a negative role. So with the air entrainment, wave speed is gradually reduced, and the air bubble is able to absorb a lot of transient energy. So under a normal condition, the pipe is full of water. So when water pressure drops, water column separates, and water evaporates to form the air cavity. So when air cavity grows, air vacuum valves can emit outside air into the pipe system to mitigate the negative pressure. So after some time, water column will rejoin and air will be forced out of systems through the air release valve. So usually the collapse of air cavity will produce a huge pressure spike. And the two phases flow, water and air flow, when the cavitation occurs. It is simulated through the DVCM, which is a discrete vapor cavity model. As two-phase flow simulation usually has a lot of assumptions, so the simulation results are usually not reliable after cavitation occurs. Therefore, so in the technical community in the US, we always tell the users that when we see the cavitation happens, we need to know how cavitation happens and how to prevent it from happening. So in order to mitigate the surge impacts effectively, we first need to fully understand how a specific water system behaves. So the tool is just a tool. We are not able to expect this tool will give you the solution or a strategy just one shot. It takes time. It needs a lot of effort, for the modelers or engineers to fully understand their system. Yeah, first thing. So first we need to identify, there are three lines for the hydraulic system. The first one is a grade line, hydraulic grade line. Grade line, which is the elevation, elevation change, along the pipeline. The other line is a hydraulic grade line, which is a hydraulic, the head, and it's going up and down along the pipeline. The other line is the maximum downsurge. So with that Joukowsky equation, we are able to see to get an estimate of the potential downsurge or potential upsurge. So potential downsurge, we need to draw a line of that, which is a dashed line here. That is the potential downsurge. So in this diagram, we are able to see the hydraulic grade line is in the minus the C over G delta VO. We are able to see, to identify some part of the pipeline. It's above grade line and some is below. If for those the dashed line is below the dashed line here, if it's below the black lines, it means it's a huge negative pressure potential, even cavitation. So, and next we need to figure out the three terms, time-related terms. The first one is a reflection time. So in this diagram, we are able to see on the right side we have reservoir. On the left side, we have a water treatment plant, and it pumps water from water treatment plant to a reservoir. So the distance, the L is the distance from the water treatment plant to the reservoir, and then we also have wave speed. So we are able to get the reflection time or response time of 2L over C. So that's a really important term that we can use to mitigate the system. And then we also need to in the previous slide, we mentioned that we need to focus on the uncontrollable transient events, which is pump trip, because of power outage. So we need to really know how the pump behaves. For example, like rundown time. So how long for the pump to run down, to spin down from full speed to 0 speed, how long it takes. Usually it's 1 second or even less than 1 second, very small volume. Okay. The other important time related term is a valve closure time. So that is controllable. We are able to see how we operate the valve, from fully open to fully closed. Yeah, that is the closing time. So with those time terms, we are able to to figure out how to control our system, how to evaluate the system through those 3 time terms. So next we can talk about the surge protection strategies. So here I want to say that luckily, the assumption of Joukowsky equation is not true. Not everything happens at the same time. We still have some space to mitigate the surge protection of transient events. So we can play with time, the time terms, because there are 3 important times, like response time, rundown time, or valve closure time. And then we can use surge protection devices to prevent the high and low pressure. So next to a pump station, it's highly recommended to use a closed surge tank, such here. Closed surge tank. It is used for the high, when pressure is high, it can, absorb some water. And when pressure is low, it can provide water. So usually the closed surge tank, it has, kind of half and half, half air, half water. So it's very effective to protect the pump station and also protect the whole system. And then we are able to see the pressure relief valve. That is just, once the pressure is really high, we can just, release some high pressure water in order to mitigate the high pressure situation. The other important thing is air or cavitation. We have to protect the pipe system from low pressure, even cavitation. So air valves, it could be just combination of air vacuum valve or release valve altogether. So it can emit and release air airs when needed, and also expel the air out of the system in order to protect that localized area. So when we do the air valves, we need to be careful when we emit the air into the system. It has to be quickly because high pressure just happens so quickly. In the same time, we also wanted to release air in a slower mode. So we don't want to produce a high pressure because of air valve operation. So, and we also use the open surge tank for those high elevation location, because they are kind of far from reach and not able to maintain frequently. And check valves usually are very useful in the water distribution system, because in the water distribution system we have different pressure zones, and we need to, some zones are low pressure and some zones are high pressure, and then we have to use a check valve to kind of separate the 2 zones, so the pressure waves are not able to easily to spread from the high zone to the low zone, or low zone to high zone. Okay. So yeah, so there are some best practices, such as to install a closed surge tank downstream of the pump station, or to place air valves in those remote locations with with the potential to have cavitation. Those are best practices. And also we want to introduce something when we do the transient modeling. That is kind of traditional wisdom, but probably we need more caution, using those traditional wisdom. So the first one is a demand-driven approach. So what is a demand-driven approach? Demand-driven approach assumes that the demands can be met under all operating conditions, even with zero pressure or negative pressure. We know that if it's a zero pressure, we are not able to get water out of it. In negative pressure, don't even mention negative pressure. So, but research kind of show us that the demand-driven approach, the pressure insensitive, tends to over-design the transient protection devices, which results in unnecessary additional costs without offering greater protection against the hydraulic transient events. So the solution is we need to model the demands as a function of the pressure, such as head discharge relationship, parabolic, or the standard offers based methods. The next topic is about a skeletonization. So skeletonization is a process to select certain part of the pipes or the network for inclusion in the model evaluation. Skeletonization can be performed automatically or manually. In automatic technique include branch trimming or combine merge the series pipes or parallel pipes, as long as they are able to achieve the same hydraulic effects. And research showed that, it is probably true for the hydraulic simulation, but for the transient modeling, that's totally wrong. It just can distort the system from the transient modeling perspective. So solution to it is, to perform the system-wide, a full pipe system transient analysis, not to skeletonize it. The next topic is about a looped network configuration, because the loop network configuration is pretty popular in water distribution system. And loop network configuration kind of assume to improve the system's response to hydraulic transients and reduce the risk of extremely high transient pressure. It's also kind of try to build the redundancy, the multiple purposes, build a redundancy, in the highly sensitive area. But this logic, is not good sometimes, because of you built in some spatial grid, right, or loops, and then it can end up with, under some circumstances, it can end up with kind of severe or unintended transient events happen, with that kind of configuration. So, so the solution to it is to take a closer look at that loop network configuration, see how it behaves in that area. The last one is over-design. So over-design, in the civil engineering system, it kind of implies a higher degree of safety, but it is not not a safety factor in the world of the hydraulic transients. It is because of complex cycles of constructive wave transmission, reflection, interaction can cause unexpectedly high or low pressure as extra transient protection devices are activated. So just give two examples. Surge tank, closed surge tank. It's not the big elevator. No, it has to be the right size to protect the system, not a big elevator. The other one is we can install a really sophisticated surge protection device in the system, in order to mitigate some transient events. But it could end up with, if it's not set up well, it could end up with, a kind of more severe transient events, happening or produced by that device. Okay, so next, let's cover this Joukowsky equation, because it's kind of very important. It's also the first and initial assessment of the hydraulic, transient. Joukowsky usually kind of refer as the basic water hammer equation, or we call it the instantaneous water hammer equation, or maximum kind of theoretical water hammer equation. So it is a conceptually simple relation used to describe the pressure rise resulting from the sudden stop or start of the fluid flowing in a uniform pipeline in which differences between the initial and final state is known. So this equation has been used as the first approximation for more than a century, long time. And then practicing engineers traditionally falsely kind of overlook the limitation of this equation and assume it's always predict the right one, the correct and the maximum possible transient pressure in the hydraulic system. Yeah, it is an easy and reliable way to determine the instantaneous pressure rise that occur only only just under some situation like a really quick valve closure, or the pump just shut down just quickly, really quickly. So it has a lot of limitations. It only applies to single pipelines. It's only no material change, the constant material, constant diameter, and constant thickness, uniform pipe friction, and there's no wave reflection. So that's really important. In the system, in the hydraulic system, we are able to play with time term, right? So we are able to expect a negative or opposite reflected wave come back, to mitigate the newly generated waves. And assume no cavitation, no gas release, no trapped gas, or no line packing, those things. So using this Joukowsky just for the initial assessment, we have to make effort. We need to spend time to know the system in a better way through all kinds of tools, including Importer Pro or any other kind of transient modeling tools. So, and then I will quickly go through our Importer Pro, how to do. So this is just for a single pipeline modeling. And later, Nathan will cover the full system, full hydraulic network, full network system modeling. So for the single pipeline modeling, we will introduce the basic steps of transient modeling. So first, we need to identify the boundary conditions. Where should it start? Where should it end? Right? The single pipe, it covers from the low point to high point, and then it has a reservoir in both ends. We also need to determine the initial condition. For example, the system is under high stress with the full speed pump and maximum demand. So that's the initial condition that can cause a lot of transient issue. Next, for other settings, we need to calculate the wave speed for pipes. We also need to specify the delta X, the length tolerance. We also need to figure out the cavitation head, in different elevation. I live in Colorado, so the cavitation head is a little bit higher. So, and lastly, we need to specify the duration, usually in seconds, and time step, and some other user settings. So once the simulation settings are done, we can go ahead to set up the transient events. To set up a transient event, we can go to the pump. For pump, we can go to the pump search data window to select the options. So for example, here the options are does it have a bypass? Does it have a check valve installed? Check valve installed to prevent the pump reverse flow. And do we want to model it through the pump file? And then, pump file is just an option. We don't need to specify the pump speed change. It is just, the Importer Pro info search. It will just figure out, the pump speed change from a pump file. And for the speed option, we can specify the speed change curve, and also pump trip. Pump trip means using the pump file to figure out the pump speed dynamics. The pump speed means we already know the how pump changes speed. We can just insert the speed change. For example, like here, it takes 2 seconds to ramp down from 1 to 0. Yeah, and for the pump trip, it's we just specified the option here, and then we don't need to we don't need to provide a pump speed change. For a valve closure, we use this is a valve closure. So go to this. We can also kind of specify, does it have any bypass line? Does it have any check valve? Because some are really critical control valve. They need to have a check valve to to prevent the reverse flow or to protect the critical facility. And then for the valve. Modeling the control valves, first we need to assign a kind of convert these valve as a TCV, throttle control valve, and we assigned a minor loss coefficient curve to it on the right. So it will, this curve determines the minor loss given the percent open, and then we specify a kind of valve stem change curve, which is shown here. So this one describe how the valve stem change. So for example, like this one, this valve kind of stays open, 100% open, and it stays open for 2 seconds, and then it takes 10 seconds to close down to fully closed position. So once we set it up, we are able to review the model results. So we need to verify if the model result represent the initial condition correctly. For example, the pump flow, the pipe flow, are they reasonable? And then we can do like a hydraulic run only to verify their flow are the same. And once the initial condition is verified, and we can view the pressure profile using the InfoSurge's graph. We have a graph called a surge pressure profile. So it will show the the high pressure, low pressure, and also elevation of the pipe. Okay. And once the model results are available, we are able to do a lot of review. There are a lot of review tools such as a single element time series graph and model element tabular report. So here I want to highlight two widely used reports. One is a surgeon node range report, the other is surgeon node group graph. So those reports are a must, when we do transient modeling. So the surgeon node range report, so we are able to, to find where the high pressure occurs and where low pressure occurs, just doing the, the sorting. The other review tool is on the right, which is surgeon node group graphs. So we are able to see how pressure wave travel, here and there, right, in different time. So in that, we are also able to see when the high pressure occurs. For example, here, it occurs here, and when the low pressure occurs, which is here, and it's also a cavitation occurrence. And InfoWater Pro also provides a tool called a surge animation. And then from where we are able to see the high pressure envelope and check where the cavitation occurs. So here we are able to see this is how the pressure kind of going up and down, along the pipeline. We are able to see in the high elevation, it has cavitation potential. So when this thing happens, we need to figure out how to mitigate it, how to prevent it from happening. So cavitation head is just a line that is calculated, which, the pressure is now able to go below. And then from there, we are able to see the bounce. We are able to see additional severe pressure wave created from that. So where to find that, we can use the surgeon node range report. And when it happens, we can use the surgeon node group graph to figure it out. And how to mitigate it, just I mentioned, a few minutes ago, we can, install the closed surge tank next to the pump station, and we can install the air valves at high points. Okay, with that, I will hand it over to Nathan.
Okay, thanks, Sean. So Sean, if you stop sharing, I'll be able to share my screen. Thanks. All right, and okay. All right, you should be able to see my screen.
Yes, I see it.
Thanks. Okay, so thank you, Sean. So we've just looked at the theory, and you've walked us through how you can model surge events along a single pipeline and within InfoWater Pro. And now I'm going to walk through an example of setting up surge modeling within a full system, a full water distribution system inside of InfoWater Pro. So I'll follow these steps in a logical order. So first, I'll be starting from the point of having an existing calibrated hydraulic model, which should be the starting point for any surge event. You would need to get obviously a model with all of your pipes and demands, and it would need to be calibrated. And from there, you'll need to make some changes to adapt the model to be ready for surge modeling. So I'll show what that looks like. And then we will configure the event. An event could, obviously include a pump shutdown, a pipe burst, a sudden valve closure, etc. Some event that causes a surge, and then we can run the analysis and assess the impact, looking at graphs, profiles, maps, and so on. So once we understand the impact of that event, then we'll explore several different scenarios where we can mitigate that surge event using surge protection devices. And then once we have a final design or proposal for the project, I'll show how you can then publish those results and share them out with stakeholders for decision making. So stepping forward, we'll start off with adapting the model. So here we're looking at a water distribution system inside of InfoWater Pro. If you use Esri ArcGIS Pro, you will probably recognize this interface. InfoWater Pro is an extension inside of ArcGIS Pro, so you can bring any GIS data that you want to work with. This is a small city. You'll notice that there's an area of the network that's not included. That's a university. So as I start, you can select any object and graph it. And I bring up this point just to mention, you'll want to make sure you start with a calibrated model. This is, of course, just a demo model, so this is not like exact, real data, but just a reminder to, calibrate your model, make sure it's matching the pressures and flows. Otherwise, you would just be adding new assumptions on top of incorrect data. So calibrate your model.
Sorry. Nathan, sorry if I interrupt you. Someone
Yeah.
from the audience asked if it is possible to use the change the mouse pointer into some colors or use a pointer because they are interested in what you are doing here. So
Okay.
if it can be
Yeah.
more clear. Thank you very much.
Yep. Okay.
Sorry.
Thank you for stepping in. Okay, so we can start with a calibrated model, and then one of the next things. So that's a calibrated model, and then from there, once you have a calibrated model, you will also need to adapt or configure your valves to be ready. So so this can mean a few things. Sorry, where's the sorry, I can't, now that I have a, now that I'm using a laser pointer, I can't see the video controller. Hold on.
We can see the pointer, but
Yeah.
are two of them.
Yeah, okay. I just can't control the video. Well, I can just talk quickly. Sorry, let me step back.
Thank you.
Ah, man. Okay, there we go. So I guess I think I'm still one slide behind. Okay, now I can see my slides. So there we go. So now we can configure valves. So there's a few different things you can do. So if you have an active PRV, you can set it up this way. We have this active valve screen where you can set, like for a PRV, you can set the pressure set point as well as a response time. So then the valve will try to regulate how much resistance it's applying to achieve that pressure setting. And it will also have a response time, which adds a little bit of delay just to be more realistic, and that can impact how the pressure response occurs. And also another way of modeling valves is you may want to apply a time varying or interactive valve. So you can, so what you do in InfoWater Pro is you set it up as a throttle control valve, and then you can apply a stem change curve, and that will, so you really need two curves. One is a head loss versus percent open, and then the other one would be just a time series control of how open that valve is over time. So that gives you control to manage a control directly, to enforce how open it is over time. And the other option is that PRV that can achieve a certain set point. And so next, once your valves are set up, I'm going to apply a map and take a look at pressure. So one other thing for hydraulic surge modeling is that you want to make sure you avoid any negative pressure at nodes. You can review this on the map as well as in a table. So one of the things with master planning is that you often you might not care about negative pressures in traditional modeling. So like if you have a node on the suction side of a pump coming from groundwater, you probably, it doesn't actually matter if the pressure is negative computationally, because for a planning model, you only care about really the pressure on the other side. However, when we start applying a surge engine, those negative pressures are going to trigger cavitation, and it's going to cause some unwanted consequences. So you can modify your model to, for instance, lowering the elevation as appropriate, just to make sure you don't have any negative pressures anywhere. And then the next thing you could consider is, should you skeletonize your system? This word was mentioned earlier. It's, again, just simplifying your model to better handle the computational intensity. In some cases, you could skeletonize if your system is really large and complex and you only want to focus on a certain part of your system. But in many cases, within InfoWater Pro, it's not necessary. As mentioned before, when you skeletonize and you change your system, that can alter the impacts of how pressure waves reflect and travel through your network. And so sometimes that's not a good idea. And because of the wave characteristic method we use, you can often simulate pressure transients on a whole system without skeletonization. So there's always a trade-off, but just something to consider. And so now our model has been adapted sufficiently. We've adjusted our valves, and now we're ready to configure the event. So in this model, I'm just going to simulate a simultaneous power outage on this west side of the system. There's obviously many different things you could do to simulate a pipe burst event, but for this example, I'll go with a power outage, and it will impact several pumps at the same time. So that's pretty straightforward. I can select a pump and then click this outage event window, and I can just turn on a pump disturbance. So here I'm going to vary the speed, and you can just input a pump speed change curve. So in this simple example, I'm just ramping the pump speed from 1 to 0 over 1 second. So it's going from full speed to 0 within 1 second. Obviously, you could change that to be 5 seconds, or use a non-linear curve if you wanted. And in the interest of time, you could do that for all of the pumps. You could do it in a table in bulk view if you wanted. For this video, I just highlight that I've already made that change on these 4 pumps. So these pumps all have an active speed change. And once I've done that, now I'm going to run the analysis. So you can click this run window. We have a bunch of different run types. If you click on the surge tab, you get this window that we've seen before on one of the slides. I'm going to turn on pressure sensitive demand, and you can control that pipe segment length tolerance. So I'm just going to pause it right here. This is the parameter that controls how it kind of impacts the time step that the engine chooses based on the waves. And so a larger number is going to obviously, it's going to compute much faster. If you want to go smaller, you'll get higher resolution with your results, but it's going to take longer. As we've talked with engineers, oftentimes they'll start with a pipe segment tolerance length, typically in real world systems of around 25 feet, maybe as a starting point, and then you may want to test lower and see if you get different results, knowing that that's going to take a longer time. It's one of those parameters you can test higher ends, test on the lower end. Is that additional computational time, does it provide a meaningful value? And there's a number of other settings that are available. I'll move along in the interest of time, but if you have any questions on any of these, feel free to enter them in the chat and we can address them later on. So once you set that, I'm going to click run, and then my results are now available. So I can go to a junction and click graph. Here you can see the pressure, and it drops to very low pressures. It bottoms out, so that's that cavitation event. So we're definitely getting some cavitation, some bad pressure impacts. And you can also create a profile. So I'm going to click from one node to another. The software will figure out the shortest path in between those 2 points, and then you can create a profile view of that point. And this will show you the maximum head and minimum head, and that green line that kind of squiggled around really quickly, that will show you the pressure or head at the current time step. And as I click play, it will animate. You could slow it down if you want, but you can see how that moves up and down as the pressure waves propagate. The ground level is showing as the yellow line. So anytime the green line goes below the yellow line, you're at high risk for cavitation. And in addition to looking at a graph and a profile view, you can of course also create maps. And being inside of ArcGIS Pro, you have a lot of mapping functionality that you can build out and share. So here I'm going to look at low pressures across my whole system. And so now you can see how far did those low pressure waves travel into the system. So you can see in this case, the extreme low pressures are mostly just on that western side of the system, but it's useful to know where that is. And one of the values of modeling this on your whole system is that sometimes the worst impacts are not always just downstream of your pump. For example, your high pressures could be the worst at low elevation points in your system, and your high and your low pressure impacts could be the worst at different high elevation locations in your system, which might not be right close by to your pump station. So it's always useful to bear that in mind, and that's why we can simulate over a whole system. So now that we know that there is pretty bad pressure impacts, let's explore some ways that we can solve this. So within InfoWater Pro, we can create multiple scenarios. This is the Scenario Explorer. You get a tree view where you can explore a series or a branch of different what if cases. So in this case, I've modeled my surge outage, and now I'm going to create several different scenarios underneath where I'm going to try out different surge protection devices. And then I can pick and compare which is the best surge mitigation strategy that I may want to do. So here I'm going to just enter a name. I'll use this acronym SPD for surge protection device. So I create a scenario. I can also give it a surge data set so that any changes I make are going to be specific to that scenario. And then now I'm going to select the junction just downstream of my pump, and I can turn on surge protection device. So then we get this window. There's a number of different device types, and each device type you select, you'll get a number of related parameters that you can modify. So this initial device that came up is a simple air valve. It's a 1 to 2 stage air vacuum valve. These can be useful at high elevation points, as mentioned, for air release valve or as an air vacuum valve. Sorry, that jumped forward. But there are a few other types. So as I select it, you can enter in any numbers that you want to. You can vary, for instance, the initial air volume, since it's a multi-stage. So there's 11 different types you can choose from. As Sean had mentioned, it's common to put a closed surge tank downstream of pumps. So that's what I'll enter here. Closed surge tanks, can handle the higher pressure right downstream of the pump. And then once I've done that, I just rerun. And with the new results, if I open my graph, I just click refresh to load the latest graph, latest data into the results. And you can see that pressure response has now gotten a little bit better, but it still does get pretty low at certain points. So I'm gonna just maximize this graph. And here you can see multiple different scenarios at that one location that I'm observing. So the yellow dashed line was our initial surge event. That's kind of the worst case event. The blue line was the one that I just implemented, where I applied that closed surge tank. If you remember, there were 4 pumps that had the power outage. So when I just apply one surge tank, it solves the issue locally, but it looks like there's definitely cavitation still in that zone somewhere, and that's causing these spiky results. So the other 2 surge scenarios that I set up outside of the recording, those have this red dashed line and green dashed line. Sorry if it's not very easy to see. So the red dashed line keeps the pressure above 15 psi. The green one does the best, but that could also be a more expensive solution. So you can weigh out different options and explore as many alternatives as you want. And if you check into our help file, we outline and summarize a number of these different surge protection devices that you can use. You can pick different ones, obviously, for a host of different reasons, as Sean had mentioned. Some are good for handling those high pressure spikes downstream of pump stations. Some are better for relieving low pressure, and so on. And so finally, since we're in ArcGIS Pro, there's a lot of different maps you can do. And so here's an example where I have created separate layers for these different scenario strategies, and it can be useful to compare the scenarios also spatially. So here I'm using a swipe tool to just swipe in between 2 different scenarios to see the before and after of different pressure surge devices. So that gives you a good spatial understanding of how the system responds. And finally, once you're at the stage and you're ready to share out your results with others, one example you have being inside of ArcGIS Pro is to share these maps to an online ArcGIS Online format. So here I could just right-click any of these layers, share it as a web layer, and then that will share out the results and data from my model to a web map. And then once you come into ArcGIS Online, there's a lot of things you can do. So for example, I'm going to add one of the layers that I've created within my organization. So I'm going to add the pipes as a background layer. Initially, they come out on top of my results, so I'll just drag them down. And in addition, you can see that if I click on one of these points, I can see the results that I chose to share out. And you can also toggle on and off the visibility. So here I can see after I apply surge protection device strategy number 1 or surge protection device strategy number 2, you can see spatially the advantages of each of those options in an easy web format that you can share out with stakeholders for easier project delivery. And so with that kind of concludes the full walkthrough of what you can do in InfoWater Pro. Before we get into Q&A, just wanted to share out some additional resources to be aware of. So as part of Autodesk, we have a lot of support for education. So if you are a student or if you're an educator, a professor, we have a program where you can access our licenses for free. If you go to autodesk.com education/home, you can read more about the education eligibility terms, and then you can sign up and get a free license for a year that you can renew. And that's available for most Autodesk software, including InfoWater Pro and InfoWorks WS Pro, those two products that I mentioned earlier. So we're always happy to work with the education space. In addition, we also have free on-demand training. So if you go to autodesk.com/learn, you can access libraries of our different training modules on different software, including InfoWater Pro and InfoWorks WS Pro. You'll just create an account, but then you can track your progress through different learning modules. As you get into, you could cover the basics of InfoWater Pro, as well as if you want to jump straight into surge modeling, you can jump to that module, and then you can see all the different topics that we cover within surge modeling. And you can then access training videos, sample models with step-by-step instructions. Just some other resources to be aware of. If you're interested in water in general, we have a One Water blog where we talk about different things that come up in the industry related to our different software. And one other related topic, we did a case study with a consultant at Hazen and Sawyer recently. So that recording is published and available, where she walks through how she uses InfoWater Pro for modeling full water distribution systems, and she talks through some of the experience and tips and tricks that she has learned over time using InfoWater Pro. And finally, these are just some other resources. These are not our own. These are just general resources that we have used and leveraged and recommend. So with that concludes the content that we have, and we invite you to use the Q&A.
Thank you both, Sean and Nathan, for your presentation. It was very interesting. I've seen that Sean already answered to some questions. There is the first question was, can you comment on the accuracy of the Lagrangian approach used by InfoWater compared with the MOC? Does it always produce consistent results, or does it have some limitations compared with the MOC? I don't know.
Yeah, Katerina. So thank you for reading it out loud. Yeah. So I try not to, answer it, because of it. It's a lot of discussion, in terms of this. So, okay. So the question is, does the WCM or Lagrangian method produce the consistent results, or the same result as MOC? I had the same question when I joined Innovyze, or now Autodesk, 2011. It's been 14 years. So at the beginning, I also thought it's too easy, right? Why is it so easy to do it this way? But as time goes, I've been working with a lot of users, a lot of applications, utilities. So I feel like it is, I have high confidence that the Lagrangian approach will produce the consistent results as MOC with much less computing power consumed. So so I'm confident. So what kind of degree? Okay, so if I'm given, because the water distribution system is really simple, just fully pressurized water. Okay, fully pressurized water. As long as there is no air coming in through the cavitation, the results between all the boundary condition, initial conditions, in all the simulation settings are the same. comparable between the MOC and WCM, the results should be comparable, should be pretty close to each other. Okay, so when the cavitation occurs, as I mentioned in the presentation, the method to to simulate the air in water mix two-phase flow, that based on a lot of assumptions and then a lot of numerical treatments. So it could be very it could be a little bit different. So we like to, as long as the cavitation occurs, the results after it is kind of not reliable. It's hard to verify those results are correct or not. Similar thing applies to MOC. So, okay. So please reach out to us, Nathan and me. We have our email address. We will maybe share it later. And then we can talk more about it. I hope, everybody would be more confident about it. So.
Thank you very much. We have some more questions. Someone asks, how about the license for ArcGIS Pro?
Nathan, do you want to go ahead?
Yeah. So yeah, to use InfoWater Pro, you do need ArcGIS Pro, and Esri has similar programs for education. If you're within a university or a student, you can often get licenses through Esri for ArcGIS Pro. That is a requirement. If you're not able to get that, you could also try our other software, InfoWorks WS Pro, which does not depend upon Esri. I also see there's a question, can you show how to bring up the multiple graphs? I think I can
Yes.
bring that up if I can recall. Yeah, since I don't have the software open right now with surge results. So after I run, you can load results, and then as I graph the results from here, I can click on this button to go to reference graph, and then I click other reference sources, and then it will provide me a list of all of the different simulation results that are available that have surge results that I could bring in, because it detects this is a pressure surge graph. So which other simulations have outputs that are compatible, and I can just select any that I want to bring in and click OK, and then they'll display directly on the graph. So thanks for that question.
Thank you. I would like to exploit the fact that you have this presentation below, because previously someone asked how it was possible to set a different value for the wave speed for different pipes. Sean already answered that each pipe can have its own wave speed. I don't know if you want to show how it can be set.
Yeah, I'm not
Nathan,
sure
you
that
need to open InfoWater Pro.
Yeah.
Sorry.
Yeah, no problem.
Oh, yeah, go ahead, Nathan.
Yeah, so this model, yeah, fortunately don't have a model that's open with surge on it, but you can select any pipe, and here I can see the parameters of the pipe, diameter, roughness, and so on. And the surge tools are right here. So if I click on pipe wave speed, I can enter a specific wave speed per pipe. You can also enter a global wave speed. So if I go into the run manager, if I want to run surge, I can enter a global wave speed. So you can enter a value that's just used everywhere by default, and then any pipe that has a wave speed assigned to it will use that value. And we also have a calculator. Here we have a lookup tool where you can you could pick different materials. Obviously, we're covering water distribution, and then you can pick different pipe materials, such as stainless steel. And then if you input, let's just say like a 12-inch diameter with a 0.5-inch thickness, and you can choose how it's anchored, then I can click compute, and that will give me an estimated wave speed for that pipe material. And so you can use this calculator as you're entering in values. You could also enter the values for the pipes, importing them through GIS or via table view. And we have a number of other lookup tables and calculators. I believe, Sean, you developed this over time. So it's useful to have these quick equations and lookups as you're setting up and configuring surge analysis.
Thank you very much. Another question. What do you think is the best way to model the boundary between a pressurized force main and the gravity sewer in InfoWater Pro?
Sean?
Okay, so like I mentioned a few minutes ago, the InfoWater Pro or in InfoSurge is a module of InfoWater Pro. So InfoSurge assume everything should be pressurized. And it's better to be just water, not air. But if it does have air, it's okay. A little bit is okay, but not much. So that is not doable with it probably require another tool to do it.
Thank you very much. There was another question before that Sean already answered, but I would like to recall it. Could you please clarify whether it is possible to simulate the transient both upstream and downstream of a PRV by imposing opening and closing times on it? Because Sean answered yes, it is doable in InfoWater Pro. I don't know if you, Nathan, want to show practically how to do it. I mean, if there is a PRV and it should react to pressure waves, for example, no? So does it move? Does waves pass through it?
Okay. So yeah, I just addressed that question from just that paragraph. Maybe behind that paragraph, maybe there are some specific situations we need to consider. But we can talk more. We are really open to any questions. We not guarantee we can have an answer, but we like to discuss it, and hopefully the whole community is able to know it more and know it deeper. So with the PRV, Nathan mentioned, this is the way we do it. We first convert this PRV as a TCV, and then the PRV as a TCV, right? And this valve has a kind of flow in head loss relationship, and we kind of characterize it through this minor loss coefficient curve. So it means each percent open of the valve, it has a minor loss. And then we specify the opening time or closing time, any kind of specific, maybe increase, decrease in terms of opening. We can all kind of characterize it in the stem change curve in the middle diagram. And then combine those two, we are able to see the InfoWater will control the control valve, stem position, and then use those flow head loss relationship to to do the wave calculation, and then we'll end up with upstream pressure and downstream pressure both. Yeah. So and also upstream flow and downstream flow. So it's a fundamental feature or function of this InfoWater Pro.
Okay, thanks.
Yeah.
One more quick question. Here questions are rising. Can you explain the CV setting for inertial effects?
Okay, sure. I will answer live. So yeah, so Nathan, if you go 2 slides up, we are able to see one more up. Oh yeah, here. So yeah, so here we have there's on the bottom right, there's something called a parameter called a CV setting for the inertial effects. Yeah, that's the question. So the check valve, in order to protect the pump or control valves, but it has some side effects. It could produce more transient events, kind of the check valve slam effects. And then the manufacturer produced some more advanced check valve to prevent that situation. So for example, if it already closed a lot, right? But close 90%, only 10% open, it would just go ahead to close it. no longer just depends on the pressure difference, upstream, downstream, right, to open it or close it. And the check valve close is kind of, close incrementally. It's not just close it, or open is open, it's incrementally. It divided into, delta, and then close it, step by step. And then when it reaches to certain, for example, like if we use 0.8, it kind of, when it close 80%, it will close all the way to, to the fully closed position. So
Okay,
I hope it answers.
Thank you
the
very
question.
much.
Yeah.
Another question. Can you give more details on how demands are transformed to pressure-dependent demands for surge analysis? Is it converting constant demands to emitter demands?
Kind of, yeah, that's right. So in the middle of this slide, the run manager, we are able to see the, Nathan, can you move the cursor to that pressure sensitive demand? So that's the option to make the demand as a pressure sensitive. So how to do it? So it will, so we run the standard simulation to, we run the hydraulic simulation to get the pressure, to get the demand, right? With that, we are able to calculate the emitter coefficient, just based on pressure flow relationship, and use that as the as a parameter, to control the flow, not control the demand as up and down, right, based on the pressure. Okay.
Okay, thank you. And is it possible to use QGs instead of ArcGIS Pro?
No,
Go ahead,
yeah,
Nathan.
InfoWater Pro is only built as an extension of ArcGIS Pro. So yeah, you won't be able to use QGIS.
Okay, thank you very much. I don't know if there are more questions. Yes. Nathan mentioned about using a calibrated model for surge analysis. Does it mean calibrating the model against steady state or quasi-steady state data?
Yeah, Sean, do you want to comment?
Okay. So yeah, so the surge analysis is really sensitive, especially for the water distribution system. There are a lot of pipes, a lot of pressure zones, a lot of control valve, a lot of pumps. Even in the single pump station, there are multiple, small and middle and larger pumps, right, or VSP pumps. So it's very sensitive, and we need to get a really, really baseline, the initial condition right. And then a right initial condition relies on a calibrated model. And calibrated model means, it reflects the reality really well. So I calibrated to against the steady state, against to a condition that you really like to they really like to do surge analysis. For example, it could be a high demand day, right? A max day, max consumption day. It could be all pumps are running, all pumps are running. We pick some situation or some events or some time, some conditions, and then we make sure the model produce the flow, the pressure, kind of follow that, kind of, roughly or match that, expectation, so that's what it means for the calibrated model. So yeah, just make sure our initial condition, it is correct. It reflects the real world condition. And at the same time, also make sure once the surge analysis run is done, right, that the final state is also reflected, yeah.
Yeah. So for surge analysis, we'd only use one, kind of a steady state from your standard simulation, but there are many benefits to having calibrated your model in a more dynamic, time varying or extended period simulation, so that you have confidence that your model can represent, conditions at midnight, 7 a.m., 8 p.m., just the range of conditions. It's better if you can get your model to that point, to be able to model surge at different times of the day easily.
Okay, thank you very much. It seems like we have no more questions for you. Thank you very much for, oh, no. one moment. How is attenuation of surge wave incorporated during surge analysis?
Okay.
Very
So I addressed this question once. So attenuation of surge waves. So when there is a wave generated, it will travel to a junction, to a pump, to a valve, and then it will be reflected, it will be transmitted, and then keep traveling, to create more waves. And then that the reflection and transmission, that will reduce, they will change the wave magnitude. Okay, so that's one thing. The other thing is when the wave kind of travel throughout the pipe, the friction effect would be considered. So it would reduce, the magnitude according to certain parameters. So probably it will go into really detailed, technical details about it, but it does consider it, yeah. In my last answer, I kind of put my email address there so we can, just reach out or send us an email. So my email is sean.huang@autodesk.com. And then Nathan's email is nathan.gertz@autodesk.com. So send us email. We are happy to, communicate, to share all knowledge that we have.
Thank you very much. I think we can close this first part of this session. And I remind you that we now can have a short coffee break, and the session will start again at 15:20 CET time, okay? So enjoy this coffee break. See you later.
Okay, thank you.
Thank you all.
Thank you.
Bye.
Thank you, Sean and Nathan.
Thank you, Katerina. Bye.
Okay, welcome back again. I think we are ready to start the second part. Okay, so let's move to the second presentation that will introduce two open source tools developed by the University of Texas at Austin to address the challenge of transient flow modeling in water networks. For me, it's an honor to introduce the speakers who will talk about this. First of all, Dr. Lina Sela, who is an associate professor at the University of Texas at Austin. Dr. Sela's research focuses on improving the efficiency of water distribution system facing current challenges by integrating digital information from distributed sensing devices with models. She's an associate editor in the prestigious Journal of Water Resources Planning and Management, and she is a recipient of the National Science Foundation Career Award. Dr. Sela will be joined by Dr. Luke Singh and Dr. Gerardo Riano. Dr. Luke Singh is a senior data scientist at Xylem with a PhD obtained at the University of Texas at Austin. Her work focuses on numerical modeling and algorithm development to address challenges such as water loss management and Internet of Things for water system management. Dr. Gerardo Riano is a postdoctoral associate at Cornell Tech with a PhD at the University of Texas at Austin. Dr. Riano's interests lie in the field of digital twins, water energy nexus, anomaly detection, and water system management. Moreover, he is the primary developer and maintainer of MapSwim and PSTNet. So that's all. Dr. Sela, Dr. Singh, and Dr. Riano, thank you for being here, first of all, and the screen is yours.
Thank you, Valentina, for the great introduction. We're very excited to be here. Lou, do you want to share your screen?
Can you see my screen?
Yeah.
Everything is fine.
All right.
Okay.
Move to the. All right, perfect. So Valentina just introduced the three of us. So what I'd like to do is just to give a brief introduction of on work and the motivation for our work, and then I'll pass it to Lou and Gerardo to present their work. So our plan for today is to kind of spend half of the time introducing TSNet, which is a transient simulation water networks, and then transition to PTSNet, which is a parallel transient simulation water networks. And then we'll be definitely happy to take questions. So everything we'll present today is publicly available, has been published in previous journals and also publicly available. So here I have a few, we have a few citations, and we'll definitely show a few more links as we go forward. So before we jump into TSNet, just wanted to share a few works that we did in our group that are related to transients and kind of what prompted us to develop these tools. So there's definitely many applications of transients, and definitely don't need to give the whole overview to this group. But some of the works that we've done before primarily were focusing on modeling and monitoring transients in distribution systems, and really more on the focus on large scale systems. So the slides you see here is a system in Singapore where there were pressure sensors installed. And the two figures you see at the bottom, they show modeling results, which are the red lines, and then also the simulation results. So this is kind of an earlier work that we did that showed that by monitoring transients at very high frequency, there is potential to use this information to detecting pipe bursts. Some of our more later work, if you can move to the next slide, please. Thank you. So here we also did some work collaborating with the city of Austin, where we had several pressure sensors installed in the distribution system, where we were continuously monitoring high frequency pressures and moving them around the system to capture the different types of transients that we were observing. Some of the work that Lou did at her PhD was focused on detecting those transients and also characterizing the different types of up and down surges, different shapes and frequencies and so forth. And that information was useful to assess what are the potential damaging impacts of the transients that we observe in the system. And then the next slide, just one more example where we use transient information. So we utilize this information for sensor placement to improve localization of events. There's definitely a lot of work on sensor placement in water distribution systems, but the unique feature that we focused on here is to use the different features of the transient signal, so we can improve not just the detection of the event, but also the localization. So if you think about this intuitively, if we look at the magnitude or the rate of the drop, this gives us different features about the system, about the events. So if we detect one, it helps us also localize what is the origin of the event. So these are like very briefly 3 applications that we did in our group that have to do with transients. And then essentially, if we can move please to the next slide. So by working with these real problems and real systems, we kind of realized that we had a challenge to continue developing more sophisticated methods and decision-making tools, because we found ourselves limited with what we can do with modeling. And essentially, we just felt the need to have a simulation tool that would be flexible to the specific application that we're looking into applying. Also that it will allow us to automate simulation, and it will be flexible enough to customize different specific things that we would need. So that's essentially the reason why we decided to develop TSNet first and then PTSNet, to basically have a tool that would be open source, available, used in Python, because this is being more and more used and applied in everywhere essentially. We wanted to make sure that that tool is easy to use for users that are already familiar with tools like EPNet and Winter, because most of the researchers who are focusing on water systems analysis, they're familiar with these tools. So we wanted to make it very user-friendly. And we use Python because it can also be integrated with other applications and other softwares that are publicly available, and also make sure that this can be continued to be extended, adopted, and improved. So this is kind of the motivation for developing these tools, which was very exciting for us. And I will now pass it on to Lou to present first TSNet, and then Gerardo will talk about PTSNet.
Yeah, thank you, Lina, for setting up the stage. So TSNet stands for Transient Simulation Network. So this was the package that was designed in 2019 and 2020, around that time frame. And I will start by talking about the governing equations and the numerical method we used in TSNet, the behind the scene. And then I will start showing some examples of how to work with TSNet for different scenarios. And I just want to make it sure that this is clear. The TSNet is fully open source. It's on the source code is on GitHub. It has its documentation and everything. It's open source, meaning you can download it, also meaning you can contribute to it. So if you see something that if you want some feature that is not in there, feel free to fork it and make changes. And if you want to merge it to main, do a PR. I may not be like very quick in review that, but I will try my best to see to make it merge if that's a feature that we wanted in the main. And so first of all, I want to start with all the commercial transient softwares. There are, Bentley, KY Pipe, InfoSearch, maybe there are more. So these are very fantastic software. It has a very easy, user-friendly GUI, and it has extended model capabilities like search tank, different pumps, different valves, all those things that we love. And it can be integrated with GIS, which make, the prep work much easier. And so those are the good thing about it. But when I was, working with this as a PhD student, I found them, first of all, expensive for to purchase the license, and secondly, it's sometimes can be difficult to extract and analyze and visualize the results. Meaning, like, I can't really write I mean, I can, but it's not very straightforward to write a Python script to, get the results and iterate over that. And also, it's a little challenging to run simulations systematically. For example, when I was working on the sensor placement, I wanted to run a lot of simulations. I know we can run batch simulation, but it's still like not very straightforward to me at that point of time. And then most importantly, those are closed sourced. So users cannot really modify, add, and customize the functions. Also, it doesn't interact very well with programming software like Python. Maybe I feel things might already changed since 2020, but this was the pain point where we were facing when at that time frame when working with transient related problems. So again, that's what motivated us to build a lightweight open source package that especially for academic usage, is easier to interact and play with. So yeah, here's just a screenshot of TSNet in the Python package repository, so that you can just install it like any other Python package through pip install or any other environment management tool that you use. And the documentation is also public. I thought it's very nicely written. Especially this was my first project developing Python package, but there is definitely room to improve. So again, it's open source. If you see something that you would like to improve, go ahead and do that. Yeah, so we didn't invent any new method in this package. So all the numerical tools, the discretization, the governing equations are well documented in this publications, in these books. So we were just implementing that in Python and making it public available. So down to the governing equations. Most of you guys in this call are probably very familiar with it already, about water-Hammer equation. And the way we discretize it is using method of characteristic along the characteristic line C plus and C minus. And a key parameter of this equation is wave speed, which is not needed in steady state simulation, but very important in transient simulation. So the wave speed can be calculated with this equation, and so this will be taken as an input to TSNet. So meaning TSNet would not calculate this for you, but you calculate it beforehand and give it to TSNet. And in terms of friction models, back in the time frame where this developed, again, there are still ongoing kind of research on what friction models is the best. And we started with the simplest quasi-steady friction model, and embedded into the MOC discretization. We also implemented the unsteady friction model. Also included in the MOC discretization, as you can see, this unsteady friction model kind of added in a lot of complexity in the equation by judging the length of the equation. And also, if we later on we will look at the simulation time, we will see that it makes the simulation more computational expensive. And in terms of the demand model, we use pressure driven, and it's only pressure driven. So I got question for me like, can we make it demand driven? The question is, I'm not sure if the person is in this call, but the answer is like currently it only supports pressure driven, because back in the time our thinking was this is like transient is a very short living event, and having a fixed demand doesn't make sense in our mind. So we were hoping this is just a pressure driven demand that changes due to along with the pressure wave caused by the transient events. So in terms of boundary conditions, we support pumps, valves, burst, leaks, demand paths, surge tanks. So I wanted to mention that we don't have the support for different types of pumps, different types of valve. Is, for example, do I have the slide now? For the valve, we kind of had a curve that is a public valve curve for gate valve. And that was the one we had embedded in TSNet, and that is a default valve model. But again, if you are playing with different types of valve, or your valve has very different curve, just put it into, you don't even need to put into TSNet, but just when you run the simulation, give it the specific valve curve, so that it will be tailored to the valve model that you are working with. In terms of pump, we were modeling the shut off and spinning up of a pump, but we with only one pump curve again. And if you want to play with other pump curves, you will need to make changes on your own. But again, the bottom line is we want to like offer a basic support for all these models, all these elements that are very common in a water network. And also the event burst leaks, those very common things that we will need. Those are all there. Fine-tuning will be needed when the use case get more serious. So in terms of TSNet capabilities, first of all, the input will be an IMP file, and it create a water network model. This is like an object in TSNet that based on this IMP file. And it can generate transient events by operating valves and pumps, shutting off, shutting down. And we can also add disruptive events like pipe burst, leakage, and demand passes into the model to simulate that how the transient event look like in those scenarios. We can also add surge protection devices such as surge tank, air chamber, to see like how these protection devices can elevate the transient magnitude. And also we can choose between the different friction models, steady, quasi-steady, and unsteady friction models. Last but not least, we can visualize and post-processing results pretty easily. Yeah, so during the development process, we did the sanity check by comparing our results with Bentley hammer. So these are the results that I'm going to show. Is on the left is for pump shut off. This is on different junctions, different colors stand for different junctions, different location of the network. And the TSNet is a solid line, Hammer is dash line. So we see a pretty reasonable match between these two. The same story on the right for burst. It's not a perfect match because we were using different time steps, different parameters, but just as sanity check, it matches reasonably. And this is the same for valve closure comparison. On the left is TSNet, on the right is Hammer. I think the reason why we didn't plot it on the same plot is just too busy to tell anything. So it just side by side view. But again, it's not perfect match, but reasonably close. And if we look at the magnitude of the transient and the general shape. Yeah, so those are the basic introduction about TSNet. Do you have any question? I kind of want to take question as I go along. If just ask your question in the Q&A or just unmute yourself. I'm not sure how we want to do that, but please ask your questions. If not, do I see something here?
We will go to question at the end. So
Okay,
they will
sounds good. Okay.
write down in the Q&A and then at the end we are going to answer them.
Great, thumbs up. So then I will go to the implementation detail. Here's a GitHub page that I put together for the demo purpose. So this is not the same repo as the TSNet package repo, even though in there's also some examples that you can look at. But here I can put them into Jupyter notebook so that we can look at it together. And if we scroll down into the README file, we can see some, installation and content. Today, what we are going to look at is this icon. Can you still see my screen? Are you seeing the web page, the GitHub page, or still the?
Yes, we do. Yeah.
Yeah.
Okay, sounds great. Thank you. Today what we are going to work on is this binder, launch binder. So that's essentially Docker environment where I put all the Jupyter notebook and the requirement in there. If you want to, open it up and do it together, feel free to do so. Let me see. Can I put a link here? Anyhow, I don't think I can send the message to everyone. I can't, right? I can't send a message to everyone.
Okay.
Anyhow, this is
I believe that only some of us can.
okay.
Yes,
Okay,
but
that's all right.
figure it out.
Yeah, that's all right. So I will stay here for a minute if you want to type this in your browser. And what we are going to do is we're going to click on this launch binder. And I already clicked it, so I'm already. Okay, so it's not very reliable, by the way. I was trying to prepare and get it connected, but maybe let me do that again with you.
And maybe
So
I'll just add in the meantime, sorry, Lo. It's just if you use this binder, then you don't have to install anything. It would just run in the cloud, so you can follow along if you choose to, and you just don't have to install anything on your machine.
Yeah. So this is like a container, virtual container that has all the requirements or a package already installed. But if later on, if you want to work on your own project, do pip install, etc. on your own environment. This is just for demo purpose. So yeah, the topics I'm gonna go through is, first of all, I'm going to go over a notebook in this binder thingy to show how we get started with TSNet. Then I would show you how to work with online document. This is kind of the how how to fish kind of thing, like how to search on the documentation to find the useful information in order to do your own analysis. And then I will just go through very quickly about the other scenarios. I will not show the code, but rather go through the slides, but the code is in this repo. So, okay, I'm here now, and let me see if I have slides about this. Okay, let me go through first a few more slides before I go into the code. So then here is an overview of TSNet, and it's the use cases that we are going to talk about today. The first one we'll do, I'm not sure which one, but I will not number them anymore. Like here is an example of valve closure, and we can do leakage, burst, and we can also do pump shutdown. So the framework of working with TSNet is, first of all, we give it an IMP file and ask it to create a transient model. And then we set up some parameters that are not in the IMP file, such as wave speed, time step. And then we define what kind of transient events we want to simulate. Whether it's a valve closure, it's a pump shutoff, startup, or a burst leak, demand pass, you name it, define it, and then define the protection devices, if any, like open or closed surge tanks. And then calculate the initial condition with winter simulator. And then define the friction model. Options are steady, quasi-steady, and steady. And then here is where we run the transient simulation with Mesto characteristic simulator. And the final stage is we get the results, plot it, store it, do anything you want with it. So the first step, okay, now we go to the first example of getting started. So we are going to start with this small network. We'll call it TSNet1. It has other names, but here its name is TSNet1. And then we are going to demonstrate how to import TSNet, how to generate a transient model, set wave speed, set time step, simulation period, do the initial condition calculation. By the way, initial condition is just a steady state where we start. And then create the transient event and run the event and plot simulation results. So this is a very brief review. If you can follow it, don't worry, we'll go to the code. Okay, so now we go, let me see, yeah. Now we go to this code here. Okay, so if we open this up, I will skip this. It's the same thing as what we went through in the slide. So here is what we do. First step, we import TSNet. The reason why we can directly import it is because we already defined all the requirement in this requirement text, and it's this binder thing has already installed everything for us. So then we say this is a TSNet. This is a network file. If we open it up, let's see. This is just the standard IMP file. And let's read that. And then we define a wave speed. Here I just give it a number of 1200 meter per second. Again, this can be calculated using the equation or other method, or if you have experiment, put in your results. So this is just a random number that not random because it's pretty standard wave speed, but again it can change it based on your use case. And define the time option. Here I define the simulation period at 20 seconds because transient event is typically very short-lived, and 20 seconds might not capture all this event, but will capture a good part of it. And it will calculate the time step for us. This is a default time step. This is kind of the longest time step. MOC would our discretization method will allow. If I put a shorter time step, it will give an error. And then we set valve closure. So here is a screenshot of the documentation on like how we set this valve closure. First of all, we give the name of the valve that we want to close. And then we set the rule. The rule include the duration it takes to close this valve, and when we want to start that closure, and what is the final open percentage. If we want to fully close a valve, that means the final open percentage is 0. And the closure constant, this is a unitless number, but is essentially this m. This is like the exponent of whether we want to close it linearly or quadratically or the other way. So for example, here I'm plotting like m equal 1, meaning we want to close this valve linearly from the start time to the end time. And the red is m equal 2, which is just a quadratic curve from the closure start time to the end time. And then here the last parameter is what I talked about, is a curve. So this is like the maybe I should go to my slide. Okay, go to this. Yeah, here. So this is a valve curve. We had a default valve curve at gate valve. This is found in this book, 2099 hydraulic pipe system. So this, if we don't give a curve, then it will use this default curve, but you can give it a curve. So now all these are in the documentation, by the way. So I'm just taking screenshots. And then we can run this thing. So now I want to take 5 seconds to close this valve. I start the, start over. I want to start the closure from the 5 second, meaning 0 to 5 seconds is a steady state. We shouldn't expect much changes in the pressure and the flow, etc. And then we want to spend 1 second to close this valve. So 5 seconds to 6 seconds is when we do the closure. And the end open percentage is 0, meaning we want to fully close this valve. And then 2 is the constant, that's meaning we use this red curve. And then we say valve closure, give it this valve name. My valve name is just valve, so it has a very straightforward name, and then the rule I give it to it, and now I would need to initialize the steady simulation. the initial condition is just a steady state simulation using the IMP file. We use Winter to do it. And it's at this time, the T0 equals 0 is when we want to have the steady state. This meaning, like, if in the MB file we have a demand pattern, this will take the 0 time step or demand to calculate the initial condition. But if you specify it at a later time, it will take that later demand to do the initial condition. So we will do that, and it also tells us we will have 86 time step in this simulation for this 20 second. And then here is where we start the transient. It give this, progress of the run. This is a very quick run because it's a very small system, and we use a relatively large time step. The first line, it gives a simulation estimate. This is 0.2 second. So that's why it's sort of instant. But if it's a larger model, it will say like 10 minutes. I have seen 10 minutes, so it's it just give you kind of idea of how long this will take. And then so after this step, the simulation is done, the transient simulation is done, all the results are stored. Where these are stored, it will be stored in this object. Maybe I should make it larger. This TSNet transient model will be stored. And here, how it organizes it has the node results for head, emitter discharge, actual demand discharge. And then for link result, it has a head at the start node, flow rate at the start node, flow velocity at the start node, flow rate at the start node, and head, flow rate, flow velocity at the end node as well. So here I'm going to show an example of how to plot the results. So here, let's say we want to visualize the head at these 4 nodes. We can define the nodes and use the method of get node, and then use node.head to plot the head. So if I run this, I would get this, the color corresponding to the color on this figure. So we can see N7. Let me make it smaller again. It occupied the whole screen now. So we can see N7 is the one closest to the valve. So that's where it first sees this event, and has a surge in the head. And if we look at N3, N3 is sort of the furthest away from the valve, hence is the last one to be affected. So this is that. And then we can actually, so we use the lines to plot these results. It's already pretty straightforward if you ask me. And then we can even have a simpler way to plot the head, because this is like, I have done those lines so many times, and I would like just a one-liner to do all of those. So it's embedded in TSNet. We can say plot node head. This is a method in TSNet, and we can give it a list of the node that we want to plot. So if I run this, I would essentially get the same results. It just I have less control over the time, the color schema, and those things. We can also visualize velocity at the start and end node. So for example, here I want to visualize this start and end node of this pipe P7, which is directly connected to the valve. So I say, I want this pipe, give me that pipe, and what I want to plot is pipe.start node velocity and the pipe.end node velocity. So if I do that, I will get these results. The end node is just jumping from whatever the steady state is to 0, because this is end node is essentially the valve, so it's a sharp close, and because we fully close it, so the velocity dropped to 0, and the start node has some fluctuation due to water hammer. So yeah, so the example that I just showed is if I just want to remind, like we were closing the valve only during 1 second, so we can call that's what, let's say that is a quick closure. Maybe we can close it even faster, but let's say 1 second is called quick closure. And if we here, I'm just doing the same thing, exactly the same thing. Only difference is I say I want to take 3 seconds to close this valve, which is a slower closure. And I'm not going to go through this one again. I'll just run this chunk of code. And we will get the results on the same node. We will see a slower and a slower transient. If we compare, for example, and 7, here this node, it has the pressure had jumped to at most 120, and that peak reaches around 8 seconds. Versus if we go to the previous results, it's same for N7. The amplitude is above 120 meter, and it happened, the peak reaches around 6 seconds. So the result is intuitive, like a slower valve closure means a slower transient, a smaller transient. The same, we will read the same, we can read the same message from the velocity plot. So yeah, so this, if we go back to the slide, this is the first thing I wanted to show about how to work with TSNet using this example. And then the next thing I wanted to show you is about the online documentation. So if like this is not mystery, like everything's documented. If you want to run something, just search it on the documentation. As a matter of fact, I haven't really worked on this for so many times, for so many years, for 2-3 years. So what I do when I work with this again is I go to the documentation and search. So for example, if we say we want to simulate a burst, then we just go here and type burst. And here in the result, we can see the example application. This is an example in the TSNet repo. Again, not the demo repo. These are two different things, just to be clear. If the demo repo only contains Jupyter notebooks. And then we can see like the comparison with Hammer, and then the most useful thing might be this API documentation on @burst. Yeah, so this is the first results, the example, and then yeah, here is where we want to look at for the API documentation on how to add a burst. We will need to specify the node of the burst where we want to have the burst, and then the burst start time, the time for burst to fully develop, and the final burst coefficients. And yeah, this is a content, a table of content for the documentation. It includes majority of things that I know about TSNet. So again, here is also a history of TSNet. So the last release is in 2020. So it has been 2.5 years. A lot of has happened in the.
I think we want to make sure that we can also talk about PTSNet. So
yeah, so sorry about that. So
I know it's exciting, so am I. So just want to make sure that we can also talk about
that. I will skip through the slides very quickly. So the rest of the thing are the most important thing I have already shown. One is example, one is how to search on the online documentation, and the rest is essentially different scenarios. The notebook are all in the repo in the GitHub, and this the explanation of each of this method, each of this function are in the documentation. So one thing, maybe this is one more thing that I want to touch, is in the initial condition calculation, there is the pressure-driven and demand-driven option. But again, this is only for the initial condition calculation. For the actual transient simulation, we only support pressure-driven. Yeah, so this is a pump shot of, again, plot results, selecting time steps. So time step is much shorter in transient simulation comparing with steady state. And I will not go into this too much. Yeah, and so here maybe there is an example in the repo that compares different time step. So that like if we give it too big of time step, for example, 1 second, it will give an error. If we use too small time step, it would take much longer to run. Yeah. So I just wanted to show the table maybe. Yes, so here within default time steps, it takes like about 2 minutes to run this example. By the way, this is a larger network. And if we use like a very much smaller time step, it will take much longer to run. So I would be careful of using too small time step. Using default is what I would recommend. And then comparing the results looks reasonably close. And working with the results, so this is one thing that I wanted to mention is when the network gets bigger, running this can take time. So you don't need to run it every time. If you have a result that you're happy with, store it in an object function, and the next time when you want to look at it and process it, open it up and use Pico to load it, and you can work with the results from there. Friction model is another thing, like steady friction, quasi-steady, unsteady, and the results are here. Again, quasi-steady takes much longer time, like 3 times longer than the unsteady. This is an area I think maybe some improvements are needed. Again, Ernesto will Rado will talk about, sorry about that. Rado will talk about PTSNet, and we will see much better time there. Common warnings, when the time is too large, it will not take it. Again, those are common error that comes from TSNet. I will not go into too much of a detail. This was designed for a much longer workshop, so that's why I cannot run over time. So I wanted to, I'm not sure if we will share this slide. Maybe I think we will, Lina, right? You will be able to look into this later on. this, I think we can maybe just reiterate it one more time. The TSNet is to address the challenge of difficulty to extract and analyze results, and address the difficulty of running systematic simulations. So, but it's when it was born, it's really designed for academic use. We are really happy to see it in other use cases, but some twist and some additional attention would be needed. Yeah, I have run over my time. So Gerardo, do you want to take over?
For sure. Thank you, Lou. Thank you so much. So I'm going to share my screen if you don't mind. That way it's easy for me to share a demo that I have prepared for the presentation. And give me 1 second. Great. Well, thank you so much. As I said, I will be talking about PTSNet, and you can think about this as the evolution of TSNet. As Lou, during my PhD, I was particularly interested in hydraulic transients, and especially the challenge that comes with computational expenses that arise when you try to scale the algorithm to realistic networks that like the one I'm showing on the right side of the slide. So it is not uncommon to see that water distribution networks today have tens, if not hundreds of thousands of pipes and nodes. And when you try to run the method of characteristics in these networks, it can be very challenging. So with that motivation in mind, we ask ourselves, can we speed up transient models by solving them in parallel using multiple computers, and also making sure that we don't lose accuracy? Because as some of you may know, there are different tricks and alternative methods that you can use to solve transient simulations. There are tricks like skeletonization, which requires reducing the size of the network, finding an equivalent system, or there are methods that find approximations to the simulation of pipes using lumped elements like the wave plan method or the wave characteristics methods. But these methods, all of them trade off speed for accuracy. So we decided to use MOC as a baseline, not only because it's the basis for all of these alternative methods to solve transient simulations, but also because the equations are well known, the numerical scheme is stable, and we are solving continuity and momentum equations, which Lou already described. And the cool thing about MOC is that, well, as I said, the numerical scheme and the numerical method is very stable and is guaranteed to be stable as long as you satisfy a numerical condition, which is the CFL condition. And it means that we need to make sure that the numerical grid that we design for our system has a particular dimension. And so what we are going to do with MOC, many of you already know of this, but I just want to recap to have this in mind, is that for every pipe, we are going to discretize our pipe in segments of size delta x. And we are also going to discretize our solution in time, defining a time step delta t. So the CFL condition states that delta x over delta t has to be less than or equal to the wave speed, which is the velocity at which pressure waves travel across the pipe. And this is necessary to be able to track how pressure waves are moving across the pipe. So that we can solve very easily, but then when you try to execute MOC in a network with different types of elements, the problem becomes a little bit more challenging because you have different types of boundary conditions. You have reservoirs, pumps, you also have protections, leaks, and you also have demands. And the thing is that the way MOC is traditionally solved is by executing equations or finding a solution to flow rates and heads for each of the elements in the system sequentially. So you first find a solution for your reservoir, for example, then for each of the pipes, then the pumps, and so on and so forth. And this is inefficient and it takes a lot of time. And this is how both commercial and open source packages are modeled. And we already talked about the necessity for open source packages, but I want to highlight that there is also a need for commercial packages to run faster and to scale. And that is the pain that we are solving with PTSNet. And the way we solve it is by utilizing and leveraging very common techniques that are using high performance computing to accelerate code. So we are using two techniques that are which are vectorization and distributed parallel computing. And basically what we do with vectorization is we take advantage of vector instructions that are optimized in modern processors to compute multiple mathematical operations simultaneously. And that way, in a fraction of the time, we can execute MOC faster. And then with distributed parallel computing, what we are doing is we are breaking down the problem of hydraulic transients. So we're breaking down our distribution network and giving a piece of the network to different processors. Each of them will compute individually a piece of the problem, exchange information with each other, and to gather results. And in that way, we can also compute MOC in a fraction of the time. So with those two, I'm going to explain you what it means in terms of the numerical method. So we are not solving for PTSNet, we are not solving a different type of equations. We are using the same set of equations that Lou described. We are not inventing anything new, but what we are improving is the algorithm that we use to solve these equations. So we achieve better computational performance. With vectorization, what we are doing is, I'm going to use this network as an example. We have 7 pipes and different types of boundary conditions. And as I said, to take advantage of vector operations at the core level, we need to arrange the information that we use to compute MOC in a particular way. Basically, we need to arrange data contiguously to each other, and that's what we did. We broke down the network and we put pipes in order and made sure that the data that is used to compute heads and flow rates for each of the solution points, each of the segments in these pipes are arranged contiguously to each other so that we can compute vector operations. So as you see, the abstraction that we use in the computer is basically putting in order each of the pipes, regardless of their order or their arrangement spatially, regardless of their spatial arrangement, we just put them together in order and form a table. And that enables us to then redesign the algorithm and redefine the set of equations that we use to compute MOC. So instead of having a set of equations for each of the pipes and each of the elements in the system, what we do with PTSNet is to have a global set of equations to find the solution of heads and flow rates for all of the pipes in the system simultaneously. And that's what these equations describe. I'm not going to get into the details, but just to give you an idea of how the equations look like, this is how they look like. And as you see, is just a single line of equations to solve all the heads and flow rates in the system. And you can find more details in our publication. And there are some tricks that we use to be able to compute this in a global level. Part of it is the memory arrangement, but also another part of it is the order in which you compute the equations. So we have vector equations for pipes, junctions, valves, pumps, bursts and leaks, surge protections, and reservoirs and tanks. And as we did for TSNet, we use EPANet as the solver to get all the initial conditions that then let us run the transient simulation. And well, you can find more details about the different types of elements and the different equations that we use, but this is what we do. We aggregate all the equations in a single point to be able to compute vector operations. In terms of distributed parallel computing, as I said, for this example, what we did is to break down the system and to give a piece of the system to different processors, so each of them compute a part of the solution. And in this example, well, the partitioning involves enumerating different solution points and assigning an almost equal number of points to each processor. So in this example, we have 3 processors and around 13, 15 solution points for each processor. But then the challenge is that when you break down the problem across different processors, then information dependencies emerge. So, for example, in this side that corresponds to the numerical problem assigned to processor 1, to be able to compute heads and flow rates in the boundary conditions associated with points 13 and 16, you need information from adjacent segments 14 and 17. But the information of those segments is saved in processor 2. So at every time step, at every iteration in time, we need to exchange information between processors. So processor 1 needs to pass information about heads and flow rates, sorry about that, to processor 2. And then processor 2 also needs to communicate information to processor 1. And this is common practice when you're dealing with distributed parallel computing. But as you will see, this is an important operation because it ends up taking a lot of time when you start scaling up. So with that in mind, we verified the performance of the algorithm to make sure that it's valid numerically, and we use Bentley Hammer as our baseline as well to make a comparison. And I'm going to show you, we run many examples, small, medium-sized, large networks, and compare results with Bentley Hammer. And today I will show you the results that we got for a medium-sized network. And I'm going to focus on results for heads, pressure heads, that are generated by a transient caused by a pump shutoff. So in this system, we have a pump that is increasing the pressure head, but it's going to be shut off, and that is going to affect pressure across our system. And when we see the response in junction 16, we see that after 5 seconds, a transient is generated. And when we compare the results with Bentley Hammer, we see that there is a good match in the results. They match almost perfectly. And that gives us the confidence that the numerical scheme is working, that there are no errors in it. But there are more examples that we executed. We executed valve closures, pump shutoffs, bursts in this same system. But now we wanted to check how much better we were doing in terms of computational efficiency when executing vectorization only on a single processor, just to see how much faster we could run. And for this, we executed a simulation with a time step of 5 milliseconds, and we compare our results with TSNet and Bentley Hammer, and we recorded the simulation times for each of these simulations. And we noticed that we were running around 120 times faster than TSNet and 6 to 8 times faster than Bentley Hammer on average. So that was a significant improvement in computational performance by using just a single processor. And then we decided to take it further like to experiment further with vectorization, and we said, okay, what would happen if we artificially increase the size of the problem by using smaller and smaller time steps so that our numerical grid is larger and larger. And we realized that when comparing the sequential implementation, in this plot, I'm showing you how the simulation time changes as a function of the problem size. The problem size is defined as the number of time steps that I'm using in my simulation times the number of segments in my network. So we see that as the problem size increases, well, of course, we spend more time solving the problem for this network, but it's particularly interesting that the sequential implementation of MOC becomes more and more inefficient compared to the vectorized operations that we are doing with our package. And that's why we end up running, when we have a problem size of 10 to the 9 solution points, we end up running 172 times faster. And it's interesting also to see that the larger or the denser the numerical grid, the better the performance of the algorithm. And that is because the processor is better utilized as more computations take place. But now the big challenge. So I showed you at the beginning a benchmark network with around 12,000 nodes, 14,000 pipes, and we wanted to simulate a transient caused by a valve using our package. We tried doing so with commercial packages and compare them with PTSnet, but then when we attempted that, we noticed that the packages crashed and couldn't take the size of the problem. Also because we were not taking shortcuts in terms of the accuracy. So we modeled this system using different sizes, different problem sizes given by different time steps, 0.5 milliseconds, 1 millisecond, 1.5 milliseconds. And you see that the number of solution points increases significantly as you change the time step. So we were solving a problem with millions of solution points. And if you don't take care of memory resources in a smart way, you can very easily block your computer and the simulation will crash. And that's what we experience with commercial packages. But we were able to solve this problem using PTSnet, solving the vectorized and the distributed MOC equations. So for this problem, we simulated this large network for a time span of 20 seconds using different time steps. And we compared the simulation times for each of these experiments. So we use different numbers of processors as well to see how much better the performance was improving as we increase the number of processors. And in theory, you would expect that performance would increase or that the time would be reduced well, as you increase the number of processors, but there is like a stagnation point, and that is because of communication. So, oh, well, I also forgot to mention that we also run partial runs of this network using a sequential implementation of MOC, and we realized that if you try to solve a problem of this size using the sequential implementation of MOC, it can take around a year to be able to find a solution to just a 20-second simulation. But then with PTSnet, we can solve that in the worst case scenario for the denser numerical grid, which is the one given by tau3 in around 10,000 seconds. And in the best case scenario, in around 20 minutes. So that gives you an idea of how much better you can do by using vectorization and distributed computing. But then, as I said before, when you are exchanging information between processors, when you have multiple processors, 22, 64, then you can notice that the time, the simulation time is mostly spent in that communication process, which I'm highlighting here in blue, and not so much in solving the boundary conditions or the solutions for the segments at each pipe. And that is very interesting. Like you can spend probably 5 minutes just solving the equations, but a lot of time just exchanging data between processors. And so larger problems achieve higher speeds, as I said before, but more processors do not necessarily improve higher speeds in performance. And that is because of the exchange of information that occurs at every time step. And because of that, there is also a trade-off in terms of the number of processors that you use. And we noticed also that if you used a different system architecture, if you use a different type of processor, you get a different performance. So we ran experiments using the Stampede supercomputer at the University of Texas, at the Texas Advanced Computing Center. And we were using decent processors, Intel Xeon processors, but at the same time, we were running experiments with a common laptop with an AMD Ryzen 7 processor. When you look at the frequencies, the clock frequencies of the processors, well, you can expect an AMD processor running faster than an Intel Xeon. But then again, we run simulations increasing the number of processors for a network, and then we noticed that for the HPC, which is the Stampede supercomputer, you decrease in time as you increase the number of processors, even when you have 22. For a laptop with AMD processors, well, the laptop that we had at that time only had 8 processors. You start reducing the time as you increase the number of processors, but then the performance doesn't improve as much. And that is because different processor architectures, that is because processor architectures vary. And there are systems that are improved for communication, for data exchange between processors, and there are other systems that aren't. Supercomputers are usually optimized for performance, not only at the processor level, but also in terms of the network at the communication level. And that is probably why we see this trend of improving as we increase the number of processors compared to a laptop that is not necessarily optimized to exchange information between processors. So performance is affected by the processor architecture. That's something that we noticed. And simulations with fewer processors can run faster in PC than in HPC. And because of that, well, we develop special functionalities, not only to solve MOC, but also to extract results and also to figure out which is the best combination of time step, of number of processors that you can use for your network. And we do this so you don't have, and PTSNet does it automatically, so you don't have to worry about that. So what is PTSNet? In a nutshell, it's composed of 4 modules, a module that will let you set up your model, another for execution, another to extract results, and another one to perform analytics. So when you are setting up the model with PTSNet, again, we are interfacing with EPANet to parse network properties. And from there, we set up a model, we allocate the necessary memory to run and execute the transient simulation, and then you can run some analytics on top of that. All the results are stored in parallel, so all the processors are writing files, result files in parallel in HDF5 format, which is a well-known format in the HPC community. And if you don't know about HDA5, it's okay because we take care of the read and write operations for you. And you don't necessarily need to have experience with that or with MPI, which is the library that we use to execute PTSNet in parallel. This is a free and publicly available library. It has been downloaded 58,000 times to this date, and it's freely available. You can click on this link, or I will be sharing this later if you need it, but you can easily find it on Google. You just type PTSNet transient simulation, and you will find this GitHub repository where you can download the code, interact with it, and there are instructions to install the package and to run a few simulations. So I'm going to be running a demo and explaining you how each of these modules that are part of PTSNet operate, the model setup, the model execution, extracting results. So it happens that when you are running a simulation in PTSNet, which we will see, you can execute a simulation. You will have your results stored in RAM memory, but they will also persist in disk. So you can also save them in HDF5 format. And then when you need them, you can easily extract them using very simple syntax we are going to check out in the demo. And then when it comes to analytics, we do all the hard work for you to figure out how much error are we inducing in the simulation by having a specific time step. So you can easily check visually the error that you are introducing into the simulation at different segments of different pipe segments. And based on that, you can decide, okay, I will use a 1 millisecond time step or a 1 second time step, for example. And to solve the issue of determining the number of processors, because as you saw, it's not trivial. For some PCs, you will be better off running with a single processor, and with others, you will be probably using more than 10 processors, depending on the simulation, the size of the simulation, the size of your network. But we also help you figuring that out, and I'm going to show you how to do that. And all the files that I'm going to show you, you can find them in the GitHub repository, which, let me share it here. Switch my screen. So this is the GitHub repository where you can find easy instructions to set up to install the package and set it up. If you are familiarized with Python and if you know how to use Conda environments, it will be very easy to set it up. If not, just follow the instructions here. And if you have any questions, just feel free to reach out. I'm happy to help you set it up. It takes only 4 steps to install. And then to use it, you can run this short example. But today I want us to focus on the files that are in this folder, in the publication folder. We have 4 Jupyter notebooks where you can see how each of the modules of the package are being used. And for that, I'm going to be using Binder today. So I think Lou already showed you guys how Binder works. This is basically a cloud environment where you can execute Python and GitHub repositories. It's very easy to set it up. You just type Binder Python, and here you can enter the link of the repository, which you can find here, pressing code. Then you're going to be working on the development branch, and then you click launch. And then that's it. This Binder platform will take the public repository and set up an environment with all the dependencies that you need for you to run the codes. So you can go to the publication folder in the repository, go to the first Jupyter notebook. And here I'm presenting a basic introduction to simulate transient events using PTSNet. And we're going to be using this network as an example. It's the same network that Lou used. And just to give you a brief description of how the package works, we start defining settings. So we use a file. No, we don't use a file. We use a dictionary object to define all the settings of the simulation, the time step, the duration. And you can also select if you have an EPA-NET file with an extended period simulation, you can also define what period you want to use as your initial condition. And you can define a default wave speed for all of the pipes, but you can also define a file with the wave speed values for each of the pipes. And there are also certain conditions that need to be checked from the EPA-NET model to make sure that the simulation can effectively run with PTSNet. And to give you an example, well, I'm not going to get into the details. You can break it down yourself, and you will get certain warnings to revise your EPA-NET model. But just to give you an example, in EPA-NET, you can connect a tank, a reservoir, and a pipe through a valve. But that is not possible in PTSNet. It's necessary to have a pipe in between a tank and a valve. And that is an example of one of the conditions that can break the package. So if you run the compatibility check, so if you set this to true, so by default, you will run a compatibility check and the package will automatically tell you what needs to be fixed in EPA-NET for the model to be executed in PTSNet. And well, there are other settings you can play with. And here you can replicate some of the simulations that I showed in the slides, like the valve closure example. And it's very easy. You basically define a path for your input file. Then you create an object, a PTSNet simulation object, where you define how do you want the folder where you are going to be saving the results to be called. So you can give a specific name to a workspace folder where your results are going to be allocated. And then you can also define the input file, and that's it. You created a simulation with PTSNet. So let me run this very quick. We import the packages. And then we execute the default settings. We create a simulation. And if you can get information from the simulation object. So the duration is 20 seconds. We are going to be executing 2,600 time steps because the default time step is 0.01, 10 milliseconds. And that means we are solving a simulation with 5,000 solution points. So you can see the scale is definitely larger than what Lou was presenting before. When she was showing you this example, she was executing the simulation with 89 time steps, but here we're running with 2,000 time steps, just because we have a denser numerical grid. And when we execute the simulation, it's almost instant. It takes less than a second to execute it and to get results. So that is the power of PTSNet, and is that you can execute hundreds of times faster just because of vectorization. You can run simulations with very large networks. And at the same time, you get to see results for different types of boundary conditions, like pumps, bursts. But, and also you can have variable demands, so you can play with it. Take a look at that. I'm going to show you now how to extract results from a file. So you need to import these packages. When you are working with files that were allocated in your system, so when you execute a simulation, you will see a folder called workspaces being created in your computer. And these workspaces folder will have another folder for each of the simulations that you execute. And you can load the results in those folders. Oh, right. So we only have TNet3 first. Need to run valve. By using this object, so using the with statement, you say with the PTSNet simulation object, extracting results from whatever folder you want to check out in the workspaces. You load that as a simulation object, and that's it. You can easily extract results for your nodes, for your pipes. And if you are checking out the nodes, you can extract heads. If you're checking out the pipes, you can extract flow rates. And it's very easy. You will get a vector that you can easily plot, and we can see the results here. So as you see, you don't have to deal with the HDF5 file at all. You just use the same syntax that you would use to extract results after running the simulation to get, well, to plot and to manage the data that you need. Now, when it comes to analytics functionalities, we develop functions that allow you to visually inspect your network and see how much error is introduced if you use a specific time step. So we are going to create a simulation object, and we are going to use a time step of 0.1 seconds. And you will see how much error is introduced just by changing the time step very little. So we have this function called plot wait speed error, where you pass the simulation object, and you can save a PDF file with the image, and we can define different error intervals that we want to visually inspect. So we execute that. And for the large network that I showed you before, you can see the size of the error. So most of the error across the network with a time step of 0.1 seconds is between 10 and 40%. So it's up to the designer to determine if that is a good enough result for them or not. And I'm going to compare the same network, but using a finer resolution, 1 millisecond for the same network. These are warnings that you can dismiss. But as you can see, with 1 millisecond, the error is almost zero across all the pipes. So you can play with that before executing your simulation to say, okay, in order to get a precise simulation, I need to use a time step of this size. But then keep in mind that if you increase the resolution of the numerical simulation, well, you are solving a larger problem with a higher amount of solution points, and that is going to take a larger computational time. And then the last part is, okay, I determine my time step. How do I determine the number of processors that work best with my application? So if you're using Binder, as I said, this works on the cloud, and this will only give you access to a very cheap machine that only runs with one processor, I believe. So I have prepared a quick demonstration of the package in my laptop. Should I find that? 1 second, sorry. Running out of time. Okay, I found it. So, well, here I'm using a Mac laptop. And by the way, this package can be executed in Windows, Mac, Linux, anything. And we have tested it and it works perfectly fine. And if we go to the same script, the analytics script, I'm going to show you what this function does. Basically, you can also use a function called compute non-processors, for which you can define basically what we do to determine the number of processors that work best for your application is to do partial runs of your simulation. So the easiest way is to, sorry about that. So we are not executing all of the simulation, but we execute probably 300 steps of the simulation and then compare how much time is taking to run that with 1, 2, 3 processors. And the thing is that setting that up manually, it's a little bit cumbersome with the package. So we made it easier for you using this function, which only takes a single line of code. You just determine your simulation, define your simulation object, and then you say, compute the number of processors for this simulation. I want to check, I want to run a partial run for at most 8 processors, and I want to compare for intervals of like every 2 processors for 4 processors in the interval of 1 to 8. And let's execute a partial run of 1,000 steps. So you will see that you need to execute the following commands in your terminal to be able to run that. You can do that very easily in a Jupyter notebook. So we just copy this line of code. We use this symbol, which allows us to run terminal commands in GitHub, in Jupyter. And what this is doing is, okay, it's running a partial run of the large simulation using 1, 3, 5, and 8 processors, I believe. And then you can see the computational times. So, okay, with 1 processor, this partial run took 2 milliseconds. With 3 processors, 1.6 milliseconds, 1.3 with 5. So you can see that the number of processor, as you use more processors for this particular example, you are doing better. And then it's your choice to decide whether or not to use multiple processors for your application. So that's in a nutshell how PTSNet works. I hope that was a good introduction, and I'm happy to share more details afterwards if you are interested in learning more about the package or if you're interested in extending it. And I'm happy to answer any questions that you have as well.
Well, first of all, thank you all for this insightful presentation that introduced us this powerful open source tool. And it was great to have you here sharing your experience with the modeling of Transient. Now, yeah, we have some minutes left for questions. I'm going to read them in the Q&A box. I saw that Lou already answered some of the questions, so thank you very much. There was a discussion about requirements concerning the complexity, but Lou provided a very complete answer, so maybe we can refer to that answer. Then there was another discussion about the modeling of bursts. Yeah, if I'm not wrong. So Kuzai Khaled asked about a technical detail concerning, as I said, the modeling of bursts. I don't know if Lou, do you want to add some additional details? I saw that Kuzai Khaled answered back to you with some additional details, but I don't know, you're free to provide some additional information, or we can go to the next question. I can read maybe the answer of Kusai, the second one. So Kusai wrote down, I cannot recall exactly why he had some problem with the modeling of burst, but he remembered that the challenge for me was attempting to simulate multiple burst events, and it was not possible to automate the process of adding dummy nodes. So he had problem with adding dummy node at different location. But it would be useful to do it to create an extensive body of dataset with different leaks to develop a data-driven model to detect and locate leaks.
Yeah.
I don't know if you have something to add to it, or we can move to another point.
Maybe just very briefly,
Sure.
I think you can add dummy node with Winter or other packages. It should be straightforward, and we're only simulating burst on node, not in pipe.
Okay, thank you. Another answer already given concerned the possibility of simulating cavitation, but it was a no from Liu, and it's okay. Then we can go to the next question, because we have
Yeah, maybe we can go to the unanswered one first.
Yeah.
Okay, we can go to Juan David Guerrero Delgado question. So just out of curiosity, how is PTSNet going to integrate with the TSNet for further development? Will it be integrated into TSNet, remain separate, or will development continue solely on PTSNet? Considering that the last commit in the TSNet repository are from 2 years ago. So
I can talk about that. So PTSNet was developed completely separate from TSNet because we had to rebuild the engine of the package to make sure that we were able to run in parallel. And so it has to remain separate. Out of curiosity, also, it would be good to know, like, why would Juan like to keep it integrated? Maybe there are some missing functionalities in PTSNet that he's looking for. So I'm happy to chat afterwards if he has recommendations of further development for PTSNet.
Thank you so much. Okay, next question from a participant. Thank you so much, really a great job, first of all. A question for Gerardo. When you compare the relative error for setting the best simulation time step, I missed how this relative error was actually defined.
Right. Okay. So in MOC, when we are solving MOC, we are running something called wave speed adjustment to make sure that the numerical grid satisfies the CFL condition, and that, depending on the time step, will generate more or less error. So what we are doing is the user provides a list of values for the wave speeds that are computed with Joukowsky equation, for example, for each of the pipes. But then when we execute the wave speed adjustment given a certain time step, we compare the difference between the wave speed given by the user and the wave speed we actually use to compute the MOC. So that's how we compute the relative error.
Thank you for the clear answer. Okay, now we're done with that. Another question from a participant, kind of a board view question, maybe for Lina. Why is PTSNet a separate package tool from TSNet instead of being another solution method using the same framework? Is any of the two being actively further developed?
Thank you. That's a great question. So the first part, Gerardo kind of answered. The reason why they're completely two separate packages is because PTSNet uses completely different solution approach. So that's why it's a completely different package. About the development, I think we face a similar challenge like many other open source initiatives, and I think similar question was raised yesterday. Both Lou and Gerardo developed these tools while being PhD students, and it was funded by different projects. So at this stage, we're not actively developing this. This is open source, so we definitely welcome contributions, and we are trying to answer questions that we get through GitHub and so forth. But currently, we're not actively developing these two packages.
Thank you. Okay, a question from Mashupati Kumar Mandal. Can we use TSNet to simulate and optimize a complex hydropower system, water feeding two branched powerhouses, each having multiple turbines, having common upstream surge tank? So a very detailed situation. I don't know if, you have access to the Q&A if you want to read again the question.
Lou, do you want to take this or do you want me to answer?
Yeah.
Maybe.
So short answer, not really. Because it supports pump valve, but like the basic pump valve, not a pumping station. If you really want to use it for like system with pumping station, I would recommend, do some analysis on the pump station, collapse it into one, and go from there. But short answer, not really. Lina, please add if you have more.
Yeah, I think there are better packages to do that. Our goal was really more focusing on the propagation of these transients in the distribution network. So there are definitely better tools to, if the goal is to model transients in a pumping station in the internal processes.
Okay, very clear, thanks. One last question, I believe for Gerardo. Your parallel computing used MPI. Have you tried the OMP or even GPU?
Yes, so we tried it all actually. I think by OMP he is referring to OpenMP, which is a different approach in high performance computing, in which you are sharing the memory across processors and you don't have to communicate. The issue with OpenMP is that you cannot scale because you are restricted by the allocation of RAM memory that is available for each of those processors. And when we were running problems with millions of solution points, we realized that these networks can occupy a significant amount of RAM memory. And then OpenMP is not as efficient and you don't get that much speed up. We even tried GPUs, which are very similar to OpenMP. But the thing with GPUs is that you have thousands of small processors that actually are not as efficient as the processors that you find in a CPU, in a modern CPU. So you, like to this day, well, I believe until GPUs are significantly improved, the processor inside of a GPU is significantly improved, you cannot do much better than with a CPU for this specific problem. So yes, we tried it all, and the combination that we are proposing here was the best we worked with.
Okay, thank you for your feedback. So I believe that we have no questions left, so that's all. Thank you very much for joining us today, and see you tomorrow at 1 p.m. Central European Time for the 5th day of the course. We will have a last presentation from Bentley, but most of all, don't miss the opportunity to participate to the final roundtable that will be moderated by some leading experts in the field of transients, and will gather all the course speakers. So see you tomorrow, and thank you again.
Thank you, everybody.
Thanks.